Hello, my name is Alex Casson and I'm Professor of Biomedical Engineering at the University of Manchester. In this lecture, I'm going to give an overview of EEG technology. So I've got an example kind of EEG setup picture on the screen there, and straight away you can see why we might be interested in using this as a brain monitoring modality for looking at networks in chronic pain, studying some of the neural mechanisms that may be going on. So for this lecture, I've split it into 4 different parts. So firstly, just a general introduction, kind of what is the EEG, going into kind of more depth from the kind of picture that we've got on the screen there. And then the main part of the lecture is looking firstly at the electrodes that we use to make a connection to the scalp, because they have a very important role in determining the signal quality that we get. And then from that, moving on to look at the instrumentation that we typically use and just kind of peeking under the bonnet a little bit so that we've got some understanding of how the signal is actually collected. And then I'll conclude by speaking about some future directions and some emerging topics in this area. If you're interested in going further, I've put a couple of example references on the screen there. I might be a bit biased, but I think the top 2 are very good. They're also both available for free. There are many references in this area giving the background and theory of EEG, and I've put a couple of starter ones from other groups on the bottom of the screen there. Okay, so let me start off then by speaking about the fundamentals of EEG. What is it and why are we interested? So I think many people are familiar with what's called the ECG. So this is when we put electrodes on the chest typically, and we measure the electrical signals that occur due to the operation of the heart. And in many ways, EEG is the same, but rather than putting electrodes on the chest, we put them on the head. And so we can measure the electrical signals that arise due to the operation of the brain. Now, putting the electrodes on the head introduces some challenges. People tend to have hair on the head, and that makes the electrodes much harder to get a good connection to the body. The skull is also a very good kind of blocker of the signals, and so the signals tend to be very small, typically a few microvolts in size, and that means that the EEG is a very sensitive setup. It can be very sensitive to artifacts and other things. But fundamentally, what we're doing is we're putting electrodes on the head and we're measuring the electrical activity that we can detect there. And why EEG in particular? Because of course you can do optical-based brain monitoring, you can do magnetic-based brain monitoring. The nice thing about EEG is, well, firstly, that it's non-invasive, and also that in principle it can be portable. So we can do studies while people are in their own homes, while they're going about their daily lives. But what it is also is very widely used. So in the clinic today, people presenting for epilepsy diagnosis, for sleep disorder diagnosis would have EEG recorded quite routinely. It's used in basic science, for studies of Alzheimer's, chronic pain, as we're interested in here. And that means there's a huge amount of literature, of tools, of different instruments that we can use. And then one of the key benefits is that it's got a very high time resolution. We tend to say that EEG has a low spatial resolution. You can't fit that many electrodes on the head. But it samples very quickly, typically 200 or 500 times a second. And so that good time resolution is potentially important for some of the emerging approaches to managing chronic pain, like neurofeedback, which you're going to learn about in other lectures in this course. If you had slower modalities, you can't necessarily see what's going on in the brain quite so quickly. So in terms of setting up an EEG, the first thing to do is to get some electrodes, and we'll see some of those in a few minutes time, and connect them to the head. There's an international standard for where electrodes are usually placed. And in terms of the theory of EEG, it's important to remember that we're doing an electrical measurement. We're measuring the voltages that are present on the surface of the scalp. Now, another word you might remember from your physics classes, another word for voltage is potential difference. So it doesn't make sense to say the voltage here is 10 or whatever, right? What we have to say is the difference between two different points. And so to get one, what's called EEG channel, we need to put on two electrodes. And so one channel is the difference in voltage between two electrodes. And depending which electrodes we choose to use, we get what's called the EEG montage. There's a few different choices for which montage you use, and with different pros and cons and so on. What we tend to use these days are what are called referential montages or unipolar montages, which is to say that for the reference electrode, say I want to record the activity at a frontal site here, the reference I'm going to use, say A1, the ear in the case on the slide, I'm going to keep that reference the same for all of the different electrodes that I use. So it's not that I need two electrodes for every channel, it's that I need one more electrode than the number of channels I'm interested in recording. And actually we'll see later on that we typically have to introduce another electrode known as a driven by leg in order to make everything work. Once you've got your EEG set up and collecting data, there's a number of characteristic waveforms that we can start to identify. The EEGs is not like the ECG. For heartbeats, there's a very characteristic clear waveform. EEG signals are much smaller, much harder to interpret, but there are common features that we can start to see. So if you were to put electrodes on me now, there is of course background EEG going. I would call that free running EEG. It's the activity that is there all of the time. And so we've got kind of an example of that there. And in that free running EEG, there are features that we can potentially identify. So this is what's known as an interictal spike. So people who have epilepsy, in between seizures, they may have these features, and it's possible to spot them and help use that to help with the process of diagnosing epilepsy. There's other features. For example, when you go to sleep, there are features known as K complexes, known as slow oscillations, and a number of things that we can see directly in the time domain signals. What we tend to do a lot is take the time domain signals and decompose them into the frequency domain. I'm not going to go over how we do that. Fundamentally, we take the Fourier transform of the time domain signals. And we often look at some standardized frequency bands. So very low frequencies tend to be called the delta band. There's a lot of interest in what's called the alpha band between about 8 and 13 hertz. And these can give characteristic patterns. So if you put electrodes towards the back of your head and you close your eyes, you will see more alpha activity. And so we can start to see responses that we expect. We can use that to check that we've set up the equipment correctly, but also start to infer what is the brain state of the user. We can go a step beyond that and actually have what are called evoked responses, which is to say if I give you some stimuli, that can cause a characteristic brain response. Often we have to do that a number of times and then average the results together to kind of reduce the impact that noise have. But if you do that, you can start to see, for example, here we've got what's called an N170 response. N because it's going negative, 170 because it's occurring about 170 milliseconds after the stimulus was presented. And this is a characteristic feature when we present a face to somebody. On the bottom here, we've got examples of what's called motor imagery. So if you imagine to move your left arm versus if you imagine to move your right arm, we get different kind of characteristic responses over the motor cortex. And you can imagine this is the basis of many brain-computer interfaces. We're getting different signals in different situations that we can use for control. Now then, as I said, the EEG is a very small signal, and so we're always going to get artifacts as well. That can come from a number of different sources. It might come from muscle movement, jaw clenching. It might be environmental, and we'll touch on that a bit later. It might be coming from movement and so on. But nearly all EEG signals, and especially if they're more portable recordings, will have artifacts in them. And you'll probably have to do something to either just delete those sections of data where it's too corrupted, or do some algorithmic cleaning of the data to get a nice clean signal to be working with. To record an EEG, what we need is firstly some electrodes to connect to the scalp, and then some instrumentation to record the voltages that are present. So let's start off by looking at the electrodes that we tend to use. There are lots and lots of different types of electrodes that you can go out and buy, but we can group those into broad categories. So the kind of bog standard starting point for electrodes would be what's called a wet passive electrode. And fundamentally, that's a lump of conductive material. We tend to use silver chloride because that gets very good performance. It gets a low noise connection to the scalp, and it's got a low drift connection as well. We can get those to be either disposable or reusable, and that depends a bit on whether it's economic for us to spend the time cleaning them. Generally speaking, if you just take an electrode like we've got there and put it on the head, it won't actually make contact with the scalp. Right? It will just sit on top of the hair and you won't be able to record anything. So in a classical electrode, we add a conductive gel to it. And so this really kind of acts as a bridge, and it just helps give a electrical connection between the scalp and the electrode so that we can pick up a recording. And in most cases, this is kind of the bog standard setup that people would start with. But of course, there's a number of negatives, particularly with regards to the gel. Right? It can dry out over time, so that limits the length of your recording. But I think moreover, it just takes a long time to set up, and it leaves quite a mess at the end of a recording. And so there's been lots and lots of research into ways of not needing a gel, or not needing so much gel. The main approach for doing that would be to have what's called an active electrode. So typically with an active electrode, there is still some gel, but nowhere near so much. And what an active electrode does is it takes some of the instrumentation that we're going to hear about a little bit later, and it puts it directly on top of the electrode. And what this means is that there's less sources of interference possible. We're taking our small signal and we're amplifying it essentially as soon as we possibly can. The result is that we can tolerate a much higher contact impedance. So when we set up electrodes, we don't just put them on and hope for the best. We put them on, we can measure the quality of the contact through what's known as the electrical impedance. For a passive electrode, to get a good recording, you probably need an impedance below 10 kiloohms, probably 5 kiloohms ideally. where with an active electrode, the impedance could be more like 20, 30, 40 kilo ohms, and you'll still get good quality data coming out. Active and passive electrodes are probably the two kind of go-to commercially available electrodes that you're likely to use today. And there's then lots more that attempt to go beyond those, particularly with regards to removing the gel. So on the left here, we've got examples of what are called dry electrodes. So these aim to make contact with the scalp directly, and they tend to take a fingered approach, and so they kind of pass through the hair rather than sitting on top of it, and they can make a direct connection with the scalp. There are a number of dry electrodes that are commercially available, but it's probably fair to say that they are less widely used other than in research studies. There's been a very wide range of research going into what I would call conformal electrodes. Sometimes these are called temperature 2 electrodes, but rather than having a big bulk metal lump of some conductor, these aim to be very thin, very flexible, and so they can flex and stretch with the skin, and potentially as a result stay in place for a very long period of time. These are very much at the research stage, and they, at the moment, they're only really possible for hair-free regions of the head, but they present a very exciting future direction. Okay, so once you've got your electrodes and you've got them set up, we need to connect them to some instrumentation, something that will actually record the voltages that are present on the head. Now, in making that instrumentation, there's probably two key challenges. The first one is about noise. Remember, the EEG is a very small signal, and that means we've got to have very low noise amplifiers, or else all we'll record is electronic noise. And so making a low noise amplifier isn't trivial, and of course this is why it's taken some time to have really miniature portable units, because in general, in terms of electronics, we can make lower noise amplifiers if we're willing to let them have more power consumption, because that's going to trade off with battery life that we have. The other big challenge is around what's called common mode voltage, and we'll see this as we move through, but typically we need a third electrode to set up a basic EEG recording, and this is because your body picks up interference from the electrical environment that's around you right now, and we need to take some steps in order to handle that interference that is picked up. Before we look at the instrumentation itself, just a note that there are of course lots of standards that relate to EEG equipment. So on the right hand side here, there's a list of, if you're making your own unit, different standards that you might want to think about. If you're simply buying an off-the-shelf unit, on the left hand side, these are the factors that the IFCN think make a good EEG unit. And so you can see they've given a recommendation for the amount of low-level electronic noise that can be present. There's always going to be some noise, we can't get rid of it completely. They give a standard for, in a passive electrode case, what the impedance should be in order for there to be a good connection to the body. And these are things that you might want to bear in mind when you're comparing different units or looking to set up your own unit. Then, zooming in to the instrumentation, what we would use is what's called a biopotential amplifier. And fundamentally, this is a differential amplifier. It's going to take the difference between two electrodes and then amplify it. And then we've got some steps to make it into a signal, a digital signal, that a computer can understand, and then we can wirelessly transmit it or save it or do whatever it is we want to do with it. Now, just amplifying the difference between two signals probably isn't enough in order to get a good quality EEG. You can do, but most of the time we introduce a third electrode, which goes by a few different names. Typically it's called a driven right leg. That terminology comes from ECG, because the basic principles here apply in exactly the same way, even if the electrodes are in a different place, the signals are different sizes and so on. But the basic principles would remain. And what the DRL does, and we'll see this in more detail in a minute, is it measures the interference that is present on you, and then it applies the opposite back to try and subtract it off. The net result of that is that to set up a basic EEG recording, to get one channel, you probably need 3 electrodes. You're going to have the site you want to record from, you're going to have your reference, wherever you've put that, and then you're going to have some driven right leg as well. So to get one channel you need 3 electrodes, and then if you're using a unipolar montage, you need one more electrode for each channel that you then want to add in, because the DRL, the reference, are going to be the same ones across all of them. You don't need a separate one to be added each time. Now, what you can also see on the screen here is some of the evolution of EEG instrumentation over time. So of course, EEG units used to be very physically big. They used to have a pen writer rather than kind of storing and displaying the data digitally. And over time, with advances in computers and electronics, these things have become more and more miniature. Larger ones still have a lot of use, because sometimes it's useful to be able to record more than just the EEG. It might be that you want to be doing EEG and eye tracking, or EEG and ECG, or EEG and something else. And a nice physically big unit means you can connect all of those different wires into the same device. They often have auxiliary inputs. And if you're not going to be doing something portably, if you're not space constrained, it can be very useful to have a large kind of inpatient sized unit. Certainly for my stuff, we're much more interested in kind of portable measurements, in doing studies out of the lab, in the home environment maybe, where people get stimuli which aren't present in a clinical or research setting. And so for that, there's been available for a while now ambulatory EEG units. And these days, these are typically small enough to fit on the head itself. That's minimizing the wiring distance that's present for the electrodes. And that can help with data quality, because there's less distance for interferers to be picked up on. And fundamentally, I say they're small, they're portable, and people can move about while wearing them, if that will lead to the introduction of more artifacts in the trace, which they're going to have to do some processing to handle. Then, as we move into the more kind of research space, wearable EEG would be kind of taking the same sort of electronics and making it smaller again. And then we're kind of looking at what I would call beyond wearable devices now. Some of those kind of flexible, stretchable electronics and electrodes that we saw a few minutes ago. So I don't want to go into too much detail about the electronics, but I think it is useful to look inside a unit just a little bit. The more we know about the instrumentation and how it works, the easier it's going to be for us to kind of optimize it and get good quality EEG recordings. Fundamentally, the EEG is recorded by what's called an instrumentation amplifier. So this is a standard electronic configuration that's used in a wide number of different settings, and it takes two inputs, and as we said before, it's going to amplify the difference between those two inputs. And then this bottom amplifier here is what's going to provide our driven right leg. So let's zoom in onto that just a little bit more and we'll think about what's happening here. So what we got on the screen here is a drawing of an ideal case electrophysiological recording. It's for ECG in this case, but that's just where we've chosen to put the electrodes. Now, in reality, of course, around, certainly me right now, there's lots of electronics. And probably is for you as well, because you're watching this on a computer. Right? There's a screen, there's a computer, there's the lighting, there's the power wires for the plugs, all of that sort of stuff. So we've got some wire in the room. Let's draw it like that. And in the UK, it's got a sinusoidal signal which is at 50 Hertz. In the States, that's typically at 60 Hertz. And I'm going to get a little bit colloquial here, but it is fundamentally correct. What we have here then is we've got a conductor, which is the wiring in the room. We've got a conductor, which is your body. There's lots of electrical conductivity bits in there. And in between them, we've got an insulator, the air gap that we've got. And so what that is, if you remember some of your electronics courses, is a capacitor. A capacitor is when we've got conductor, insulator, conductor. And so although there's no direct connection, there is this kind of wireless connection between you and the 50 Hertz that is powering all of the electronics that we have. And what that means is that on your body, there's a big 50 Hertz component. Right? And if all we do is put some electrodes on you and try and record, what we'll generally record is just that 50 Hertz component. Right? It's much bigger than the actual electrical signals that we want to see. And so we need a mechanism for getting rid of that. Right? And the way we do that is by saying, actually that 50 Hertz, well, it's the same, it's more or less everywhere. So that 50 Hertz, I've got it on this electrode here, and I've got it on this electrode here. And so what we actually do is we measure the 50 Hertz. We measure what the interference is. And it's not too difficult to do that. We can get that from the internals of our amplifier. And then we invert it. So we kind of times it by -1. And then we take that inverted signal and we drive the person with the opposite of what the interference is. And then as a result, the interference kind of cancelled out, letting us record the signals that we want. If you're coming from an electronics background, this is a very classical closed loop control type situation, sort of thing that electronic engineers would learn about in an graduate course. But when you set up an EEG, it's very common, if you've not got good quality electrode connections, that all you see is 50 Hertz. Or 60 Hertz if you're in the States. And the way to get rid of that is firstly to have a driven right leg, and then secondly to make sure you've got low impedance connections to the scalp, ideally below 5 kilo ohms for a wet passive electrode. To finish off, I just wanted to say a few words firstly about EEG processing, but then also just to have a little look to the future and where we're going with some of this work. What we've looked at in detail in this lecture is firstly the electrodes that we use for collecting a signal, and then the instrumentation that lets us record that, get it into a computer. I've not gone into any detail about what we do with the signals once you've got it on a computer. That will of course vary a lot depending on what your application is. It might be that a human sits down and interprets the data. It might be that it feeds into a machine learning algorithm and it triggers an alarm or whatever. It's going to be very application specific. I think the rule of thumb is that in terms of analysing an EEG signal, if you can think of a method, it's been applied to EEG. It's a very well studied area looking at different mechanisms. The general kind of pipeline for what people would do is on the screen here, and again some starting references, because I think you could easily have an entire course, not just a lecture, a whole course on EEG signal processing. I think the key one that most people will need to look at is the artifact removal step there. There's a very well established technique known as ICA, which would be very common to take the raw data, apply ICA to it, and use that to help remove any artifacts that may have been picked up during the recording process. But as I say, I won't go into any more details than that in this lecture. Instead, let me just say a few words about things that I think are up and coming and very exciting, and things to have on your horizon scanning. So firstly, there's lots and lots of work out there about making better electrodes. It's not an easy thing to do. There's no ideal electrode. It's going to depend on where you want to record from and for how long and so on. But we've seen them a few times now, but I do think that these conformal, flexible electrodes are really exciting. They're only really for kind of hair-free regions. And as a result, we've seen lots of interest in recent years around behind the ear EEG or in-ear EEG or forehead EEG. And you can imagine, of course, that behind the ear, that's really great for, say, integrating with a hearing aid. And you can have some very potentially long-term, socially discrete monitoring of the brain. And you can see how that could let us monitor things like chronic pain in a way that we've not been able to do previously. Of course, kind of most electrodes for many studies want to be placed on haired regions. And so there's work going into how we can make those better as well. So in my lab, we've looked at personalised electrodes. So can we take some of those fingered, dry electrodes that we saw previously, but have different number of fingers, different length fingers, different shapes, to try and get the best connection through the different types of hair that different people have. There's an example on the slide from another group where the electrode that they're using is still a kind of a round, kind of standard shape electrode, but they've customized the clip and the kind of connection that's used to hold it in place to get it to connect against the skin. And I think there's a growing realization that having a 1 centimeter circular disc held in place with a cap or an adhesive isn't necessarily the best way of doing it for every different person. In my lab, we've done lots of thinking about next generation EEG hardware. And so here we've got an example where on each electrode, it's not just that it's an active electrode, where there's an amplifier on it. We've also got what's called an accelerometer. So we're measuring the movement of the electrode. And the idea being then we can use that to help us remove any artifacts that we obtain. Linked to this, of course, is trying to reduce the power consumption, reduce the size, and use the advances in microelectronics that are continuing to happen all around us to make the EEG instrumentation itself smaller, more portable, better battery life, and so on. And then lastly, it's not directly related to kind of putting electrodes on a person, But there's lots of interest now in making phantom devices to let us do more controlled testing of novel electrodes, of novel instrumentation. If we're making, say, a neurofeedback system, we can simulate it. We can put electrodes on a phantom head. The head plays out some pre-recorded EEG from the internal electrodes. We can do then real-time processing on that, and we can do everything without actually having to have a person in the loop. And so we can do some of the testing and development much more quickly. And again, I see this as a very important and timely area of future development for EEG. And that is all that I wanted to go over in this lecture. So we've seen fundamentally what the EEG is, and then had a look at the main parts of an EEG system. That is the electrodes and some of the choices and trade-offs available there. And then the instrumentation, and try to just gain some understanding of how is it actually working. And then we concluded by having a look to the future and seeing some of the future directions. Because EEG is both a well-established methodology, very widely used for getting brain data at the moment, but it's also a very active research area as we aim to make the devices smaller, more portable, and ultimately, hopefully enabling things like at-home neurofeedback, potentially at-home neurostimulation, getting information about the brain in out of the clinic situations that we've not been able to do before. Thank you all very much for coming.